Hello and welcome. In this video, we're going to be talking about frictional forces and the concepts that go along with them. So let's go on and get started. The first thing that we have to do is talk about what a frictional force is. And in physics, a frictional force is simply a force that acts against or resists motion. Another way to put this is that a frictional force is a force that acts in a direction opposite to the direction of motion of an object. So in this video, we're going to talk about two types of frictional forces: static friction and kinetic friction. So static sub S, this is the frictional force that has to be overcome just to get an object moving. And when we look at it mathematically, we get the equation that F sub S is less than mu times force normal. Now, I've done a previous video about force normal. If you haven't seen that one, I recommend that you go back and watch it so that you know what the concept of force normal is. But for static friction, force of static friction is less than mu times force normal. We'll talk about mu in just one moment. The other type of friction that we're going to talk about is that kinetic friction, or F sub K. This is the frictional force that exists even after you get an object into motion. And when we look at its equation, we get that F sub K equals mu times force normal. So that concept of mu is what we refer to as the coefficient of friction. And what mu does is it indicates to us the fraction of an object's normal force that results in a frictional force. So for example, let's say I've got an object that has a force normal of 100 newtons, and it has a coefficient of static friction of 0.5. Then that 0.5 times the normal force of 100 newtons will give me a frictional force of 50 newtons. And what that means is that I have to apply a minimum of 50 newtons of force onto that object just to get it to begin moving. So that's what's going to be required to overcome the static friction. If I increase that mass and therefore increase force normal, then let's say I now have a force normal of 200 newtons times that 0.5. I'm now going to need to apply 100 newtons of force to be able to get that object moving. So this is why we use that force of static friction is less than mu times force normal, is because as long as I'm applying a force that is less than that force of static friction, the object is not going to move. So the concept is this. Let's go back to that 100 Newton force normal and a coefficient of static friction of 0.5. I have to apply 50 newtons of force. Well, if I only apply 10 newtons of force along that horizontal, I don't get all 50 newtons of static friction at once. Otherwise, I'd have a net force of 40 newtons opposite from the applied force, and I'd see it repelling away from me. We don't see that. So the idea is, if I only apply 10 newtons of force, then only 10 newtons of static friction are applied back, so that the force in one direction equals the force in the opposite direction, and those two forces cancel out to give me a net force of 0. If I apply 20 newtons of force, I'm going to get 20 newtons of frictional force back, and again, the net force is going to be 0. Fifth of applied force. That's when static friction, in essence, says, I give up, and it allows the object to begin moving. So when you look at that formula, force of static friction is less than mu times force normal, because any force up to that force of static friction is not going to cause it to move. But once I achieve that force of static friction, that's when it first begins to move. So you may also see the equation more typically as force sub S, force of static friction, is less than or equal to mu times force normal. Because again, once you get a force applied that is equal to that force of static friction, it will begin moving. Now, force of kinetic friction, the reason why we set it equal is because as soon as it starts moving, That's what that force of friction is going to be as long as it's moving. It doesn't vary. So give you an idea down here with this setup. I've got a block on a piece of wood, and I've got a spring scale set up on it. Now, first off, again, kind of going back and reviewing over force normal. Because this object is at rest, that means that all forces in both the x and the y axis have to be equal to 0. So in the x-axis, I'm not applying any force. So it makes sense that there's no opposite force applied. So in the x, forces are 0. In the y-axis, I have the weight of that object acting downwards due to gravity. And as we talked about in the force normal video, that means I have an equal but opposite force normal upwards. So if we look at this, this is the scenario. I've got my surface, I've got force of gravity acting downwards, which equals mass times gravity, or the weight of the block, and I've got an equal but opposite force normal. So in my y-axis, my force normal is going to end up equaling 0. Or not equaling 0, sorry. Force normal will equal that force of gravity, and net force in the y will equal 0. Now along the x-axis, this is what's happening. But if I apply a force to get this moving, then as I apply that force, so I'm going to call this force applied, there's now a frictional force. And the idea is this: because it's moving, that frictional force has to be less than the force applied. Otherwise, it wouldn't move. I would have a net force opposite of the direction I'm trying to move it. So at first, with static friction, again, I start applying that force, and that static friction force is going to increase until I hit that minimum amount of force required. So this is my 100 Newton force normal, and it has a coefficient of static friction of 0.5. Then once I hit 50 newtons of applied force, I've reached the maximum static friction force, and it's going to start moving. So this would be my force of friction, which I'm just going to call F sub F. Now, if this is moving, then F sub F, or my frictional force, must be less than the force applied. And that is when this force of friction ends up becoming your kinetic friction. So to see this in action now, if I go back to this block, it's not heavy enough to really affect this spring where you can see it. So what I'm going to do is add some extra mass to it. So now my force gravity is acting on larger mass. Because force of gravity is larger, my force normal is larger. So now what that means when I'm looking at my kinetic or my static friction, mu times this force normal is going to be larger because I've increased the force normal. And that is two ways to increase static friction as well as kinetic friction, is you can either increase the mass. So for example, if I've got a coefficient of friction that's 0.5, a mass or a force normal of 100 newtons, then the force of friction will be 50. If I increase that mass and therefore the force normal to 200 newtons, still times that 0.5, now I've got 100 newtons of frictional force. So we can change the amount of frictional force by increasing the mass and therefore force normal, or by applying a force downwards to increase that force normal on the regular mass. The other way to increase force of friction is change up that coefficient of friction, that mu value. So if that mu value goes to 0.6, now for 100 Newton normal force, I have to apply 60 newtons of force to overcome the static friction. So two different ways to affect friction: either increase your force normal or decrease it, or change your coefficient of friction. But in this case, I'm going to increase my force normal. And now what I can see is on this spring scale, and it might be difficult in the video, but as I start pulling, it starts to elongate, but I still haven't started it moving. So that force that I'm applying is that force that's trying to overcome the static friction. So when I pull on this, it starts to move, and what I notice is that when it starts to move, I'm applying a force of 1.8 newtons. So that was that force of static friction. But as it starts moving, and I look at that scale, I'm only at 1.5 newtons of force, which tells me that the coefficient of kinetic friction is less than the coefficient of static friction. And that's typically the case. It's going to take more force to get something initially moving than it does to keep it moving. So if you've ever tried to move a heavy piece of furniture, maybe you've been pushing on it and it doesn't work, and then suddenly it starts moving and you kind of jolt forward. The reason is higher coefficient of static friction than what you have a coefficient of kinetic friction. So it requires more force to get it moving than it does to keep it moving. And maybe you've even had someone help you with moving the furniture, and you've made the comment to them, hey, if you can just help me get this moving, I'll be all right. Well, what you're in essence doing is talking about the fact that it requires more force to get it moving than it does to keep it moving. Okay? So that's an example of static and kinetic friction. And other thing that I want to point out is that every type of surface has its own unique coefficients of friction. If it's very rough, you typically have a very large coefficient of static friction and kinetic friction. If it's a smooth surface, it's a lower coefficient. So I'm going to take this surface now in my block, and we're going to start talking about inclined planes, because this is where normal force and frictional forces really come together. Because when I'm looking at this right now, again, I've got kind of this scenario if I push this along. But here's what I want you to notice. If I take this block and I start to incline this plane, initially that block doesn't move. And what that tells me is that that static friction is still a large enough value to be able to overcome any type of force that's directed down the plane. But if I continue to incline it, eventually it starts moving. So what exactly is going on here? Well, when you're looking at an inclined plane, and as I mentioned in the force normal video, we oftentimes think about that x-axis as always having to be along the horizontal. But when we've got an inclined plane and we start adjusting it, now my x-axis is at a diagonal. So when we look at a free body diagram of sorts for an inclined plane, here I've got my block, I've got my force of gravity that is still directed directly downwards, but my force normal, if you recall, force normal is always acting perpendicular to the surface. So as a result, my force normal is no longer in line with my force due to gravity. Instead, what I get are vector components. And we're going to look at these using two different colors, because the idea is for that force normal, it's exerting a force into that plane. That component is what's causing the frictional force. At the same time, I have a force that is acting, in essence, down the plane, and we can transpose that to here, and what we get is a nice 90-degree triangle. And the nice thing about this that makes this mathematically possible to now start to calculate is that the angle of our inclined plane equals this angle. So if we want to find for this normal force, what component of it is directed down the plane causing motion, and what component of it is directed into the plane causing a frictional force, we just have to use trigonometric functions. In other words, sine and cosine specifically, where sine is going to be opposite over your hypotenuse, which is going to be my force of gravity, or in other words, the weight of the object. And that will tell me how much force is directed down the plane. If I do cosine, Then I'm looking at my adjacent over my hypotenuse, and I can find out how much force goes into the friction. Now what I can end up doing, once I know my value of the force normal that's contributing to friction, I can put it into one of my friction equations, specifically coefficient or the static friction, and I can find out how much force I need to overcome that frictional force. I can then take my force directed down the plane, and if that force directed down the plane is greater than the force of static friction, then that block is going to move. If it's less than that force of static friction, it's going to stay still. So let's see this conceptually now. So I've got this block sitting here at this incline. And again, what you might be able to see is this idea that I've got the force normal directed perpendicular to this plane. If I move that underneath, I've made this little mark, and if I then drop a line straight downwards, you can see that there's an angle there between that line and my hand. That angle. That angle is the same angle that's down here that I just showed in the diagram. So what I can do, again, is mathematically find how much frictional force is acting into the plane, calculate that coefficient of static friction, or use this coefficient of static friction to find the frictional force, static frictional force, and then I can also find how much of that force normal is directing it down the plane. Again, if the force down the plane is less than the static frictional force, then this thing stays still. If that force is greater than that force of static friction, then it's going to move. And what happens as we continue to incline this, eventually my force directed down the plane is going to be greater than that static frictional force, and it starts moving. At which time, now I'm going to use that force down the plane times that coefficient of kinetic friction to find out how much frictional force is impeding that motion down the plane. Understanding your trigonometric functions of sine and cosine are going to be extremely important when we start calculating these two different vector components of this force normal. So that is how frictional forces act, the two different types, static friction, kinetic friction, how it works on a horizontal plane, which is fairly simple because you're not having to deal with angles, and all you're looking at is what is, in essence, the force of gravity compared to force normal. Do I have a larger force normal because I'm applying a force downwards? Do I have less of a force normal because I'm slightly pulling upwards on it? And how does that affect the frictional force as it's simply sliding back and forth? When you go to inclined planes, it becomes a little more involved because, again, now you're having to look at those trigonometric functions. So hopefully if all this has made sense. If not, and you have questions, please leave a comment and I'll get back to you as soon as possible. Also, don't forget to subscribe to this channel so you can get regular updates whenever I upload new videos. And speaking of new videos, if you please let me know. So thanks, and take care.